Welcome to Quantum Mechanics Basics. This is the part that's going to hurt your head. It hurts my head. Every time I think about it, it doesn't matter. I was introduced to these concepts almost 30 years ago now, and it still hurts my brain every time I think about it. So here we go. Let's find out why it's going to cause you a nice headache. Lesson objectives. We'll describe the two-slit experiment and how it demonstrates wave-particle duality. We'll define the Heisenberg uncertainty principle. We'll calculate values with the Heisenberg uncertainty principle. And finally, we'll define the Schrodinger equation and use it to conceptualize atomic orbitals. So what is the two-slit experiment? The two-slit experiment demonstrates both the wave and particle nature of matter on a quantum scale. This experiment is often called the double-slit experiment, which is the way it is in your book. It's extremely convincing for skeptics of quantum theory. There are many different versions of the experiment. You can either use light, like that from a laser, or an electron beam to show the effects. We're going to focus on the electron beam. That's what our graphic is for, because that is the actual experiment that they used to show this thing was a thing. All right, so in this graphic, we have electrons going towards a screen with slits. There are two small vertical slits. The slits are designed to let one electron through at a time. So they're very, very narrow. In fact, they were metal. But I digress. And then there's an optical screen on the other side of the slits. So if these electrons act like particles, we would expect to see two lines corresponding to the placement of the slits, right? Instead, we observe an interference pattern. So why an interference pattern? If you force a wave through different paths, you experience a phase shift. So in other words, it's no longer going to be lined up all as one thing. They're going to be lined up differently. And because they are no longer lined up, you get constructive and destructive interference. And so once it goes through the slit, the number of particles that hit is largest at the center, and you get fewer as you go out towards the outside. But there are far more than two lines, and they're located in areas where there are slits and where there are not slits, just like an interference pattern would show. So matter here is acting like both a wave and particle. Now, more interesting, in one iteration of this experiment, only a single electron was allowed to go through at a time, and the interference pattern still formed, even though you just put one through at a time. So it was acting like a wave, even when you only had one electron. But it gets weirder. If you track which slit the electron goes through by bouncing light off of the electron, it acts like a particle when it's detected on the screen. Doesn't matter how many electrons you put through. If you observe the electron as it goes through to show which side it went through, you get two lines like you would for a particle. The math required to model this result is the cause of many paradox-induced headaches for students to this day. So either way, these results demonstrate rather dramatically that the wave-particle duality of matter on the quantum scale exists. Also, that there is a probabilistic nature to the particle behavior on the quantum scale. There's a video version of this information linked in your book. I can't vouch for the sound quality, but the video is actually really helpful in illustrating this experiment in a visual way. So I recommend looking at it. Just know, particles do not know they're being seen. The language in that video says it knows it's being seen. No, they're hit by light waves to detect them, and that causes a difference in the results, not the particle behaving differently because it's being watched. Particles do not have a big brother complex. That is not a thing. The things used to observe other stuff in the quantum realm have similar energies and masses to the quantum realm. So I'm going to use an analogy here. When someone that is about the same size of you runs into you, both you and the person move. That's what's going on with the particles that we observe on this scale. It's unavoidable. Both things move. The effect doesn't show up macroscopically because if you were hit by a tiny little piece of dust, for example, nothing would happen to you. It's similar to the way that light hitting a baseball doesn't change the path of the baseball because the baseball is so much bigger and it weighs so much more than the light. Okay, so hopefully this makes a lot more sense. Or not a lot more sense to begin with, and when you read about it, it will make even more sense. Let's go on to trying to use math to describe these things. So Werner Heisenberg assumed that he did not need to track the trajectory of every electron, but instead focused on modeling the simple harmonic motion of a charged particle, which is kind of ballsy. Just completely ignoring all the physics that everybody else understood and saying, you know what, I'm just going to do this other thing. Anyway, he applied this to a variety of experiments and discovered that it is fundamentally impossible to know simultaneously and exactly, as in very well, both the position and the momentum of a particle. So that's delta x times delta p x is equal to delta x times m delta v. Momentum, delta p, is equal to m delta v, FYI. So you can't know both of these things at once. Now, he presented this work to somebody else, and they looked at it, and it was Max Born. He was really, really good at math, like super good at math. And he, along with Jacob Phillips and Werner Heisenberg, came up with a matrix math representation months after the original paper came out that is still used to this day. This is some pretty important stuff, and it defines the limitations of what we can and cannot know about the quantum realm. Nowadays, the matrix manipulations that they used are actually done by the computer because computers are really awesome at repetitive tasks, and that is exactly what this type of calculation is. But back in the day, being able to use a matrix by itself sped things up enormously. It was amazing. Anyway, the only other things I wanted to point out, so h bar over 2 just means h, Planck's constant, over 2 pi. And this paradox was also discovered when concerning energy and time. So there's another limitation in the quantum realm. Let's try a calculation. This math is actually reasonably easy. Just remember two things. Number one, dx, dp, dv, all of them mean the uncertainty in the measured value. And number two, when you multiply or divide by an inequality by a negative number, you have to flip the sign. This is not relevant for this example, but it's something that you should be thinking anytime you see an inequality. If I divide this by a negative number, I have to flip the sign. So what is the uncertainty in the position of an electron with a momentum of 9.5 times 10 to the negative 22nd kilograms meters per second, known to 2.5%? So what strikes you first about this question? For me, it is asking about uncertainty in position. So I automatically think of the Heisenberg uncertainty principle. So I go pull that equation. The second thing that I notice is that I'm given an amount of uncertainty in a percentage of a value, but not the percentage itself. In other words, I only have a percentage of that number to indicate uncertainty. So if I multiply the value by the uncertainty in decimal form, I will get the uncertainty in that value. So I take my 9.5 times 10 to the negative 22nd kilogram meters per second, and I multiply it by 0.025 to get 2.4 times 10 to the negative 23rd kilogram meters per second is my uncertainty. So at this point, now that I have an uncertainty, I can plug it into the Heisenberg uncertainty equation. And I do that. Okay, and I have my h bar over 2, and I'm going to solve for delta x. So I divide both sides by 2.4 times 10 to the negative 23rd kilograms meters per second. And I get 4.4 times 10 to the negative 12 meters. Now, you may be wondering, wait a second, what about the units here? Does that actually work out? I want you to remember that a joule is equal to a kilogram meter squared per second squared. Okay, so if we take a joule times a second, we have a kilogram meter squared per second squared times a second. We lose that, we lose that. We're then dividing by meters per second. And we lose this, and we lose that. So, sorry, a kilogram meter per second. So we also lose the kilogram. And we have just meters left. Huh, that's the result we wanted. Cool. It's nice when the math works. There's a reverse example of this that you see in the book, so you can use that as a reference on how to do the other way. All right, this brings us to the Schrodinger equation. 1925 was a big year for quantum mechanics. Both Heisenberg and Schrodinger were published for what we are talking about in that year. Schrodinger was a bit sadistic in his thought experiments, unlike Einstein, although Einstein has his own version of this, which is also messed up. Anyway, he makes an effective point. You have probably heard of Schrodinger's cat. So Schrodinger made an analogy between a cat in a box being poisoned and a particle being observed. So if you place a cat in a box, so that's that first box there, with a radioactive material that releases a poison, the probability of the poison being released is 50-50, let's say. The cat has a 50% chance of being alive or dead. And according to Schrodinger, it is both at once. This is known as a superposition. It is 50% alive and 50% dead. But if you open the box to find out, then you find out that there's a 100% chance of a single result. In other words, once you observe the system, the outcome becomes the only possible one. Observation changes the system. Okay, so Schrodinger said, you know what? Electrons are standing waves. Using wave functions, I will represent this by that capital Greek letter psi. And he said h psi is equal to E psi. So h with the funky tent looking thing over it is a Hamiltonian operator. This is actually a series of operations that you do on the wave function to calculate the total energy of the quantum particle. And that wave function gets displayed as a probability. So the wave function is a probability, and if you square the magnitude of that, you get where things are. It turns out we actually use imaginary numbers in wave functions, and imaginary numbers, I equals the square root of -1. It turns out that has a real world meaning, and that still also hurts my head to this day. Particles, an electron is both a wave and a particle at the same time, and in addition, oh, by the way, I has a meaning in the real world. Okay, anyway, so this is actually really kind of crazy. The Hamiltonian and indeed the wave function are represented here by the fun physics thing where you take an incredibly complex mathematics and you call it something simple and elegant. H psi equals E psi. But solving these equations for 3 dimensions requires a working knowledge of multivariate calculus, the ability to use polar coordinates readily, and a really good grasp of algebra. So when we apply this wave function concept to electrons orbiting an atom, we can calculate where the electron might be at any given point in time. We call this calculated probability function of an electron an atomic orbital. We normally represent atomic orbitals as having a solid shape with 90% confidence interval, i.e. 90% chance of finding an electron in that space, but this is not exactly what is going on. It is a simplification. So let's talk about that in the next slide. First, let's look at a 2-dimensional representation of a probability function. So you can see that we have the position x on the x-axis and the probability of finding it on the y-axis. And there are several different probability functions graphed here, but you'll notice a pattern for all of them. They are in a bell curve. Bell curve is associated with this type of function. So if you look carefully in the box in the corner of the graph, you see the width of the function is determined by the sigma value, lowercase Greek sigma, which is the uncertainty in the position. So we've come full circle, right? So Heisenberg said we've got an uncertainty in the position. Well, when we graph the probability function, we can see what that uncertainty is by the width of the normal curve that we get, the bell curve. Okay, so let's take this concept to 3 dimensions and look at the solutions for the Schrodinger equation. The numbers 1, 2, 3, and 4 on the right-hand side refer to the principal quantum number, which we'll go over a little bit later. And this representation is a cloud of electron density. So instead of giving you just the 90% confidence interval, we're going to give you the cloud and see what it looks like. So you can see that the cloud has a point where it is darkest, and it has diffuse coloring around it. This is what a probability function looks like in 3 dimensions. It's a bit of a departure from what we look at normally, which just contains the most probable spot. This is a picture of what we normally see. It looks like you stuck a bunch of balls together, but this is the 90% probability sphere, describing a number of atoms bound together in a molecule. Okay, so hopefully that gives you an idea of what the hell an atomic orbital is. Let's go forward. To summarize, the double-slit experiment shows that both light and quantum particles follow the wave-particle duality. The Heisenberg uncertainty principle says that it's fundamentally impossible to know simultaneously and exactly both the position and the momentum of a particle given by the equation delta x times delta px, where p is momentum and x is position, is greater than or equal to h bar over 2, h bar is h, Planck's constant, over 2 pi. And Schrodinger models electrons as standing waves using probability functions summarized as h psi equals e psi, and that gives us atomic orbitals when we solve those functions.